Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group meetup. So today we've got Dr. Frank Cassay, who is going to talk about call graph analysis in EVM bytecode. So Frank, before you present your slides, do you want to quickly introduce yourself?
Yes, thank you, Peter. Yeah, I'm currently working at Movement Labs. I've started a week ago, so that's very new. And I'll describe a bit later on what Movement Labs is doing. And my background is in formal verification, formal methods, and so on. So I've been in the blockchain ecosystem for 5 years now, and I'm trying to apply some rigorous techniques to make the Web3 more secure. And today, so I'm going to talk about some work related to this topic, which is about building control flow graphs for low-level code, EVM bytecode.
Oh, please present your slides. Take it away.
Yeah. So apparently I can't share my screen. It said the host has disabled the participant sharing screen.
Yeah. All these settings, advanced sharing options. Yeah, have a go now.
Yep. So hopefully you should all see my screen. I'll zoom in now. Is it okay? You see a yellow background with
Yep.
yeah, perfect.
Yeah. Looks
So
fun.
during the talk, feel free to interrupt me and ask questions anytime you think it's unclear or you would like to know more. I'll be happy to talk more about this. And if someone can monitor the chat, I'm going to minimize your faces. So right. So first things first, what Movement Labs are doing at the moment. So we are trying to build a Move-based ZK rollup on Ethereum. So Move is a programming language for smart contracts, and it was developed at Facebook in the DM Libra project, and since has been, let's say, taken by a few startups, including Aptos, Sui, who are actually implementing layer ones or layer twos using the Move language and the Move prover. So the idea is to bring safer smart contracts execution to Ethereum. So if you want to know more, you can look up at the Movement Labs documentation and website. There's lots of things going on, and it's a young project, so we are still building lots of things at the moment. So don't expect to have something fully fledged, but there's lots of very good ideas, and we hope we can develop something in the coming semester and release something. So for today, I'm going to talk more about EVM bytecode. So this is about smart contracts execution on Ethereum. And to motivate the title of the talk, which is building control flow graphs for EVM bytecode. So that was not my main motivation at the beginning. I wouldn't have done that if I hadn't needed it. So I'm going to motivate why I ended up doing these kind of things. So first, if you think about how smart contracts are developed and deployed on Ethereum, you usually write your smart contracts using Solidity, Viper, Rust, or Go, or whatever you want. And there are compilers that can compile to, at the end, what's on the right-hand side, EVM bytecode, low-level code. And there's a few tools, so you can go even through an intermediate representation. There's a few, but one of them, that's a popular one, that the Solidity compiler can generate is called Yule. And then from Yule, you can also compile to EVM bytecode. So there's quite a few options. And at the end of the day, so what I'm interested in and what people are usually interested in is you want to make sure that your contracts meet some safety requirements somehow, that there's no bug in the contracts, no bug of a certain type. So you can do the reasoning at the Solidity level, you can try to analyze the Solidity code, test it, or formally reason about it, same with Viper, Rust, or Go. But ultimately, when you compile your code, what's going to be executed is the EVM bytecode. So for instance, if there is a bug in the compiler from Solidity to EVM bytecode, then your EVM bytecode will not perform or realize the tasks that were specified by the Solidity code. The semantics will not coincide. So this is something that you would be interested to do, actually, is to try, and there are bugs actually in the compilers. There are non-bugs that are fixed on a regular basis and discovered and fixed on a regular basis. So you'd like to be able to reason about the bytecode somehow to make sure that your bytecode is not doing silly things or incorrect things. And it's hard to reason about bytecode because it's low-level code. It's usually not structured and so on. So you really have a lot of issues to deal with reasoning at this low level. So I'll show you in the next few slides what we can do to be able to reason about the bytecode. So an example here is I'm going to take my, let's say, Solidity or Yule or whatever, high-level representation, and I compile it with the Solidity compiler, and I get some sequences of bytes, which is the EVM bytecode, and I'd like to be able to reason, but formally reason about it. So an example would be, I'd like to make sure that in the EVM bytecode, you've got a stack machine. There's no stack underflow or stack overflow in my program. That's something I'd like to be able to formally prove. So not test, but formally prove. So to do so, my strategy is to say, it's not only my strategy, I should actually say that the strategy is to take the EVM bytecode and to try to embed it into a tool that can enable you to do some formal reasoning about the bytecode. And it turns out that with some of my colleagues, some of them are on this call, David, Horacio, and so on, we have developed in the last few years an EVM, so the semantics of an Ethereum virtual machine in Daphne. So we can reason about EVM bytecode, sequences of opcodes using this Daphne EVM. And there's a link that you can access to, but if you look it up, if you Google it, you'll find the Daphne EVM easily. So the idea would be to take the EVM bytecode, which is a sequence of unstructured instructions and so on, and to generate something that can be analyzed using the Daphne EVM. So that's not trivial, so I'm going to show you how it could look like. So this is this program, for instance, it's got a loop and it does some storage and return and so on. You compile it with the Solidity compiler, you get sequences of bytes, the bytecode. And to be able to reason about it, what I'd like to produce at the end of the day is a sort of, let's call it a proof object. It's an instrumented code in Daphne. So it's something that will mimic the execution of the bytecode. So you see here, for instance, that I've got a state. State number 1 is the image of state 0 after doing a push 0. So I'm just applying the semantics of the instructions here, but I do it within the Daphne EVM. So these instructions, push 0, duplicate, and so on, they are Daphne EVM instructions. And this code is some Daphne code. And if I can do that, so I embed the execution of the bytecode into the Daphne EVM, I'm able to reason about the bytecode. For instance, here, I'm able to prove that whatever is going to happen, starting from a given state, with some properties that the stack has, the capacity of the stack is larger than 2. If I execute push 0 and duplicate 1, so that's a push 0 and duplicate 1 element, then I end up in a normal state of the EVM, a non-error state. So I can prove properties about the bytecode using this Daphne EVM, right? So I'm not going to dive into the Daphne EVM. There's a few papers and so on you can have a look at. But the idea is to try and take some high-level code, get the bytecode for it, and reason about the bytecode by embedding it into some Daphne code. And to do so, I wanted to do these kind of things, and actually to produce this kind of code. So you see here that the code is split into different chunks. So there's a sort of a execution of a segment from a few instructions, and then we execute another segment of instructions and so on. So we would like to sort of mimic or retrieve the structure of the initial program if we can. And to do so as well, we need to be able to somehow find or get some properties where what the control flow is going into the bytecode, because it's not structured bytecode, it's got jumps and go-to statements somehow. So we need to recover these kind of things to be able to reason about it. So that's why as a sort of a preliminary work to generate this kind of code that I can use to reason about the bytecode. I'm going to get some information about the initial bytecode and generate what's called a control flow graph, from which I can extract this kind of proof object, and then I'll be able to reason about the bytecode. Does that make sense? Or I guess it's a yes.
Frank, so how are you choosing the segmentation?
Yes, so I'm going to talk about it, Ron. Yeah. Thank you for the question. Yeah. So I'm going to get into the details of this in the next few slides. So what I'm going to present today is first an algorithm to reconstruct, or let's say construct a control flow graph, and I'll tell you what the control flow graph is, an algorithm to do so, to demonstrate some tooling that we've been developing in the last year, and also a feature that's usually ignored in this kind of work is to verify that the graphs that I generate, our control flow graphs, are semantically correct with respect to the semantics of EVM. So how do I reconstruct or construct a graph, and what is a control flow graph? So first thing first, so if you compile this code again, this your code into bytecode, you'll get a sequence of bytes. So this is what's on the left-hand side. And you can somehow disassemble it to get a more friendly version of it. And this more friendly version says that, for instance, the 5F is the opcode for push 0, 80 is the opcode for duplicate 1. And you see on the left-hand side here, it's the program counter. So the instructions are laid out in memory next to the previous one. So this is the program counter that's progressing, and each address has an instruction associated with it. So the idea is, in the code, most of the time you execute an instruction and you go to the next one, but sometimes there are instructions that are go-to instructions or jump instructions. So there's two in this simple loop program. There's a conditional jump, so this is this one, and the conditional jump is going to use the information that's on the stack of the EVM. So the EVM is a stack machine. So the jump I instruction, the conditional jump, is going to look up the second topmost symbol or value at the top of the stack. And depending on whether it's 0 or not 0, it's going to jump to the address which is at the top of the stack. So it consumes, the execution of this operation consumes two elements at the top of the stack, the condition and the target. If the condition is true, it jumps. And if the condition is false, it goes to the next instruction in the code. So that's a conditional jump. So you will see it in the graph. You would like to see something as you execute the code, and then if the condition is true, you jump. If the condition is false, you don't jump. So you go to the next instruction. You go to the next instruction in the code. And the jump instruction here is a sort of a simple version of a conditional jump. It's a non-conditional jump. So on a jump instruction, you jump to the target address in the code, so the PC, that is at the top of the stack. So this jump here will jump to the address 0x2. So let's go back. So you see that in my graph, I execute the code, and then I jump back to 0x2. So the way I interpret the graph on the right-hand side is every segment, so to answer your question, Ron, every segment is a segment of instructions. Well, there's no jump in it, so there's no branching. So it's a linear sequence of instructions. And the semantics I apply to this graph is when there is an edge from one node of the graph to another, you execute, you first execute what's in a node of the graph sequentially. So because it's a linear sequence, you execute from the top to the bottom. And an edge like that would mean that you jump to the next one, and you execute from the first instruction to the last. And then from this one, you execute from the first instruction to the last, and then you jump back to the first instruction and so on. So that's the meaning of this kind of blocks. So in standard control flow graphs, you would have a node per instruction, but because here there's no condition or choices, there's no branching in a sequence of instructions, which is in what I call a segment. I'm going to collapse all the instructions that are together into a segment and put them together. and make sure that at the jumps or the conditional branchings only happen at the boundaries of these segments. Does that answer your question, Ron?
Yeah, thanks.
Okay, thank you. Okay, so what I'd like to do is to build this kind of graphs, and why is it useful? Because these graphs can actually be consumed by static analyzers and so on. They encode sequences of instructions. So if you want to know, for instance, whether you can reach this kind of a return statement, you would like to analyze this graph and try to check whether this node is reachable, for instance. If it's not reachable, that should probably be an issue. So you'd like to know what's happening. You can discover in the graph whether they have loops or not. So there's a loop here. But you see here that, for instance, my initial program has a loop that's going to be taken 10 times. So that's the semantics of this 10 here. But in the graph, it shows up as a loop that can be possibly iterated an arbitrary number of times. But that's perfectly fine. That's what control flow graph should be. Actually, they should be over approximating the set of executions of the program. So that's the kind of objects I would like to build, and then I'll use that to build some proof object that I can formally analyze with that. Right? So a graph, again, is going to have segments. In each segment, it's a linear sequence of instruction, and at the boundary of a segment, they can be either a jump to another segment or a conditional branching to two different nodes. So it's at most two in the set of instructions I'm using. I'm not using the new relative jumps, R jumps in the EVM, where you can branch to an arbitrary number of the children, but the code I've written actually is ready to accommodate this kind of changes. Right, so let's see what I have to do. So I would say in this first example, that was very easy, because if I know the semantics of the jump, jump I and jump, right? The possible targets of the jumps are just pushed before the instruction is executed. So it's easy to construct this graph. I just have to track what's on the top of the stack, and I'll know where the control is going to go in the next instruction. So for every instruction in a segment, again, I jump to the next instruction, and when I'm at the boundary, I have to determine where the code can go. And for a jump, a conditional one, it could go to the next instruction or to this 013 that was pushed previously. But it can be a bit more tricky. So for instance, this is another program computing the maximum of 3 numbers, and it's got a max function that computes the max of 2 numbers, but it's called twice. So in this code, you'll see that actually, so the orange part is in the bytecode is the function, the max function, and the green part is the sort of the body of the function, this mstore, and the let are just declaring variables and so on. So you see here that I've got a jump, and the jump that occurs here, actually, there's a pop before, so it pops something off the stack. So it's not easy, well, it's not obvious where the target is for this jump segment. And it turns out actually that because there's 2 calls to the max function, when you execute the code, this segment or this section of code will be executed twice, or could be executed twice. And the target of the jump here will be different depending on the call site. So that's what's reflected in this control flow graph. You see that the first jump is here, and when it jumps, it's going to jump basically after the computation of max to the computation of the value of R in the initial high-level code. So that's here. And the last time of the jump is to finish the program. So that's the equivalent of finishing the call to max here and going to storing and returning the result. So that's a difficulty in reconstructing control flow graphs, is that the target of jumps can be dynamically computed. So they are somewhere, but they're not obvious in the code. You might need to do some work to retrieve them. So in the next, let's say, a few slides, I'm going to provide a way of resolving this target of jumps. And the assumption I'm going to make is that all the jump targets that I would need in my code will be on the stack. So you can ask me a question later about that. I can give some examples as well why this is a meaningful assumption. So if I assume that all the jump targets are on the stack, then I can find a mechanism to build a control flow graph. So for the program I showed before, so I'm going to unfold the graph as much as I can. So I unfold the first segment, and here this jump, as I mentioned before, is known because it jumps to the target that has been just pushed before, 0x1b, so that's the program counter. I unfold until I arrive at a jump, and this one is not obvious. I don't really know where to jump to. And sorry. And to know this jump, so I'm going to work it backwards. So if I want to know where to jump here, so the jump instruction by definition is going to jump to the element to the target address that's at the top of the stack. So if I want to know the target address here, I'm just working backwards because there's a pop. The pop is going to pop one element on top of the stack. Then if I want to know the target of this jump, I need at the beginning of this segment to know what's not at the top of the stack, but the second topmost element of the stack. So I will use pick 0 for the top element of the stack, pick 1 for the second, pick 2 for the third, and so on. So if I want to resolve the jump here, I need to know pick 1 at the beginning of this segment. And then I can work it backwards as well. I can propagate backwards saying, okay, if I want the element pick 1 here, and it's called by this, and I come from this node, what element do I need at the top of the other segment? It's pick 2 and so on. And I work it backwards and I can resolve it by finding out that in the first segment, actually, at the end of execution, this first segment, I need pick 2, and pick 2 is the address 0x0e. So I resolve the first jump like that by working it backwards. And then I continue to unfold my graph until I hit another non-trivial jump or dynamic jump, and I'm going to do exactly the same thing, so work it backwards and so on, and then I can resolve it and I've built the full graph. So that's the idea. So the idea is that if the target of jumps are on the stack, what I'm going to do is to try and provide a sort of an abstract semantics when I'm going somehow to abstractly execute the code in these segments and keep track of some elements in the stack to be able to determine the jumps, the target of the jumps at each location. So how do I do that? So yeah, and one other thing that I should probably mention is you can see here that I've got different nodes with the same code actually. It starts at the same control location and so on. But these nodes in the graph are different nodes because they don't lead to the same future. So from this node, you've got a future in terms of control locations, which is given by this set of paths, right? Whereas from this node, it's a smaller set of paths. So I need to distinguish these two nodes. So the question as well is, how do I decide whether when I encounter the same program, the same segment, I would say, in my graph, when I unfold the graph, when I encounter the same segment, how do I merge them? Or how do I decide that they should lead to different futures so I can't merge them? So to do so, what I'm going to do is to use an abstract semantics, again, with an abstract stack. And so you see here, for instance, in this first segment, I'm pushing some values. So push 1 is pushing 1 byte onto the stack. I'm pushing some value, some values, I'm swapping them, and I'm jumping. So to be able to keep track of the jumps, what I would like to do is to keep track of the elements on the stack. And so what I could do is to record everything that's on the stack, right? That would be an easy thing. But that would actually lead to some issues later on. So what I'm going to do is to make sure that when I record what's on the stack, and that's why it's an abstract stack, it's actually something that could be a target address. And fortunately, in the EVM, that's something you can do because target addresses should be in a given set of addresses that are tagged with an instruction called a jump dest. So I know that every time I will have a jump, right, in the EVM, it should be a jump to a jump dest. So what I'm going to do here is I'm going to abstractly interpret the code. So I'm going to interpret this code and store on the stack values that are jump destinations. So only, if I look at my code, it's only a few. And the other ones, if a value like, for instance, 0x08 is pushed on the stack, I'm going to abstract it away with a question mark because I don't need it. Well, that's probably this question mark, because it's not going to be a target of a jump, right? So that's what I'm going with this abstract stack. I'm simulating the computation, tracking some interesting values that can be targets of jumps. And if I do so, so I start with an empty stack, and when I execute this code, I end up with an abstract stack, which is the top of the stack is on the left. So I don't know, I abstract the value, it's an unknown or irrelevant value. Then there's a 0x, a 0e value, and then 0x12 value. And I do that for all the computation. And it turns out that when I've got a jump here, for instance, the abstract stack, if I have defined it properly, will contain the good value that I have to jump to. And you see here that, for instance, from this code, I start with a stack which is some value, 0xe, two different values that I don't want to know the value of, 0x12. If I execute this code, I pop the top one, and then the value that's left is 0xe, and that's the target of the next jump. So I jump to this target, and I do the same for all the nodes. And this way, I'm able actually to build a control flow graph. So now what about merging nodes and so on? So you see here that these two nodes that I claimed previously were different in the graph because they led to different futures. I can now formally define why they are different. It's because that's the same code, but the context in which they execute, the stack is different for the two nodes. So I can't merge them. And I would not merge them. So that's the idea, to generate the code, the graph, sorry, to have an abstract stack. So I said a couple of seconds ago that if I would push all of the values, for instance, on the stack, it could lead to some issues, and I can quickly, let's say, mention why. So assume I do the same code, for instance, and sometimes I push some irrelevant value like 0x. So when I say irrelevant values that are not really useful to keep track of program counter and jump destinations, I could push two different values like 0x8 and 0x9, and they would be in the stack. So even if, let's say, the future, the computations are the same because the stack is 0xe, 0x12, and this will lead to the same program counter sequences. If different values were in between, I would say that these two states, maybe two states would be different, whereas actually I should be able to merge them. So I'd like to abstract away all of the irrelevant information that will not contribute to the jump targets resolution. All right, so now what's the algorithm? So I implemented it in Daphne, so I give you a sketch here, but the algorithm is basically to define the state of the graph, and the state of the graph is a segment number. So if you wish, it's a start, a PC of a segment, and the segments have been determined before, and a content of the stack. And it can also be an error state if some error happens. I'll show you later on how this can occur. But that's an abstract state. And the control flow graph algorithm, to reconstruct a control flow graph, I just do a depth first search on these abstract states. Any questions so far? Not anything related to, does it terminate or, yeah?
Yeah, Frank, yeah, I was a little unsure. So you're maintaining abstract stacks essentially at the beginning of each block. So do you have multiple stacks? Can you have multiple stacks for each block, if that makes sense? Like different context, multiple contexts for each block, effectively?
No.
So you
if you have different contexts, but a state is the code of a segment and a stack.
Right. So you can have multiple
Right.
states
So
of this.
you have multiple nodes or states in the graph,
Yeah.
but the stack can be different and the code can be the same. But they
Yeah.
are, so yeah, that I agree. That's a bit, maybe I was not clear enough, but you may, what you want to do when you build the graph is basically it's a finite state machine and it defines a language traces, right? So in these two cases, you can't really say, well, if you would merge these two nodes, your sort of control flow graph would have more path, or it would be less precise than distinguishing them. So that would still be a good graph, but less precise in terms of reasoning. So I could merge them, but that would not be a good idea if I want to perform some analysis later on. So I need to distinguish them. And to do so, I use a state which is the context, which is the stack, which somehow defines the future in terms of which blocks I'm going to, which segments I'm going to reach, and the code that's going to be executed. So by definition, right, if I have two different contexts and the same code, there will be two different nodes.
Yeah, I understand. Yeah.
Does that make sense? Or
yeah, that makes sense. Would you ever merge them? Like there are situations where actually you can you end up generating let's say different nodes, but it actually turns out the abstract stacks by just a coincidence are identical.
Yeah. So yeah. So that's a good question. So I can answer it now, actually. When I generate the graphs, I first generate this graph, and this graph is called in my generator a sort of a row or non-minimized graph. So I'm going to generate it, and then I can apply a minimization algorithm on the graph that I generate. Right. And the minimization algorithm is going to preserve the language accepted by the automaton.
Yeah, okay.
Right, yeah. So this one is safe in terms of semantics. I'm not going to merge at construction time. I'm going to merge in a later phase if I find out that these two nodes actually, well, let's say when I compute it, I don't know because the two states here are different. I don't know whether they will lead to the same future, but when I've built the whole graph, I can apply a standard minimization algorithm to merge the nodes that are encoding the same language until the end. And I implemented that as well.
Yeah. And so you mentioned termination, so I'm guessing you just iterate till you reach a fixed point. Is that what happens here?
No, I iterate to a maximum depth.
Okay.
Because I don't know whether this is going to terminate.
But presumably it should terminate because
so
jump
yeah,
destinations.
Exactly. I totally agree. So the proof again, I think, is in the pudding. My assumption is that the targets are on the stack, and I provide a maximum depth, and I run my depth first search. And at the end of the algorithm, I get a result which is yes, the maximum depth was never reached. So I could build the graph, or no, the maximum depth was reached, and then I'm going to increase it. And at some point, it should. I'll give you an example where it doesn't work, but at some point, it should be enough to. Generate the graph.
I was going to say I developed something similar to this some years ago. Right. I didn't do the exclusion bit, which is a really good innovation. And for some contracts on mainnet, it never finished because it got confused because of how the jump desks were being calculated.
Right.
It's too complicated for it.
Okay. I'll show you a couple of things that are also in the algorithm that I have implemented, but that's a sort of a well, it's a heuristic, right? So to answer your question, Peter and David's question, the assumption that the target of jumps are on the stack, and I'm going to keep track of some elements in the stack, that's a heuristic. So for instance, something that, assume I would do this kind of thing, right? I would, let's say, push, instead of pushing a return address, I would push or a target jump, I would push a target jump -1. And when I want to retrieve it, somehow I would collect it and add 1. So this wouldn't work in my scheme. This is not something that would work because I don't keep track of arithmetic on target addresses. But at the same time, who would do that? That would be a silly idea to offset and compute every time. And so it works. I've tested it on several, dozens of examples, including an ERC20, the wrapped if contract, the deposit smart contract, and so on. And it works for these contracts.
So Frank, with respect to the merging of nodes, if some of these segments do things like swap what is question marks within the stack, right?
Yes.
Then
yes.
I mean, you can't really merge those two nodes, right? You're changing the semantics of the program. Because
so I'm not. No. I'm not. So I'm applying the semantic, for instance, a swap here, right? We'll swap two elements on the stack. So if it's a question mark
but
swap
if those
with
two
this,
elements are question marks.
Yes. Then there will be, if I swap, for instance, these two elements, it will result in the same stack.
In your representation, right? But then I suppose you'd merge that with another node that's got that same abstract stack, right? But when you get there, the two elements are in a different order, and that affects the actual.
Okay. So no, but okay. So that could, I agree with you. There could be some weird things happening, but that's a heuristic. So I'm going to apply my abstract semantics and try to resolve the jumps. And that's why in the later section of this talk, I'm going to verify that my target jumps have been computed correctly.
Okay.
So, okay, see if I understand well, Ron, just confirm with me. I could make some, I could have some, let's say some target jumps that would depend on the order of these two elements. And if they are swapped, they would, so I don't see them, but the fact that they are swapped could influence the target jumps later on. So I should not say that these two states with this stack should be merged, because actually these two elements should be distinguished somehow. That could happen. But
or just if the final output is one of those elements, right? Then you're changing the semantics of the program is the issue.
Yeah, well, so I don't think I'm changing the semantics of the program, but I'm building an abstract semantics that's good enough to compute the targets, the jump targets. And if I can't find them, again, in my algorithm, right, if there is a jump, for instance, and I can't find the target of the jump on the stack, the algorithm will terminate and say, I couldn't do it. So it's a safe approach as well. It's not going to try and continue to apply it. So I can't find a target address, or it's not a target address, that's a jump destination, and so on. So I'll stop.
Do you have a formal statement of what your control flow graph sort of how it relates to the actual code?
Yeah. So there's I'll show you later on. So that's the So I'll probably, what time it is now, because I don't see it. I'll show another example actually here, which is a bit of a contrived example. But in this example, there's something happening, which is I push an element and then I iterate some loop. But what I'm going to do is that the stack is going to be such that there's the target of the jump here at the top of the stack all the time. But the stack is actually growing at each iteration. So the target of the jumps is always at the top of the stack, but I'm pushing underneath some values. Here it's 0. And the algorithm I have implemented actually has a test which is a bit more abstract than comparing two states of the two configuration or two abstract stacks. It can compare and it can check some weakest precondition and invariance of these weakest preconditions for target of jumps that will enable you to actually build the control flow graph for this program that has a potentially an unbounded stack. So I'm not going to talk too much about it, but there's a test with an invariant and a sort of a pumping invariant that can be applied, and that's applied in the algorithm for this kind of programs. Right, so maybe I should give a demo of the code. So first, the graphs that I've shown before, they were generated by the program and the interface that we developed. That was so I developed the backend of the system, which is computing the control flow graphs in a format that can be displayed. So I used the dot format. I've written the code in Daphne, so I can show you why and what are the benefits later on. But one of the benefits is that I can generate artifacts of the control flow graph generator in different languages. So you can use the Java one, the Python, the C#, the JavaScript. And one of my former colleagues, Egon, at Mantle, he developed simple interface just to demo how it works. So we called it ByteSpectre. So if I can move the Zoom window, I can try to show you how it works. I should have a ByteSpectre. Yeah, so I've already preloaded it, I would say, but so just to confirm, you can see now the screen with the ByteSpectre logo. And yes, I assume yes. So the algorithm generates the graph. So you put the code in there, you submit it, and it generates the graph. And we also annotated the semantics of the different instructions. So if you want to learn about what an instruction is doing, so this one has a tooltip, which is it's pushing white byte. This one is a jump destination, and it links to the semantics of the instruction in the Daphne EVM. So that's also something if you want to have a more precise explanation of what an instruction is doing. You can do that as well. So you can try it if you want. It's still working. It's a bit slow because we have a slow server. We haven't paid too much for it. That's why, but it's working well. And I've got a few other examples that I can demo at the end if there is some time for. But for now, so let's say I'll go back to the question that Ron asked. It could be that I have abstracted away some elements in my stack, and the control flow graph is not correct, or it could just be right. When I generate the graph, for instance, I print out a dot graph and so on, or a program, and I've got some errors in my algorithm. So what I would like to do is to verify somehow that my compiler from EVM bytecode to control flow graphs is correct or not. So I'm not going to, there's a few options. You could, let's say, write a verified compiler from EVM bytecode to control flow graphs, but I'm going to do something else, which is to have a verifying compiler. So I'm going to write the compiler from EVM bytecode to control flow graphs. And then these control flow graphs, I'm going to provide a way of checking that they are correct. And to do so, I need first to provide the definition of correctness. So that's the thing I want to do. So I've got these programs. I've computed the graph and resolved some jump targets, right? I'd like to know whether this is okay. So when I say jumps to this destination, this jumps to this destination, is it actually the case in the code? So what does it mean for a control flow graph to be correct? So you can actually formally define it. So if you're given a program, right, and you execute it, so you range over all possible inputs on the program and you execute this program. So you get a set of traces, and you collect, every time you execute, you collect sequences of program counters that you can generate from an initial input running the code. So you get all these executions, and traces is the projection of these executions on the program counters. So you can do the same for the control flow graph. You get the control flow graph, you get all the paths in the control flow graph, and you define the traces of this control flow graph to be all the sequences of program counters that you can generate following a path in the control flow graph. So the correctness of the control flow graph in terms of safety, so if I establish some safety properties on the graph, for instance, that some code is not reachable and so on, I'd like them to be satisfied on the concrete program. So if I want this, let's say this ability to translate some safety properties from the control flow graph to the actual program, what I want to do is to make sure that the traces of the program, all of the traces of the program in terms of sequences of instructions are represented in the control flow graph. So this is also easy to achieve. You would argue that if I take every block of instruction and I put a loop on it, so I do some random stuff, I say every instruction can be followed by any other, this will satisfy this predicate, but a control flow graph, to be useful, should be a bit more precise, right? So that's the idea. You could have this simple graph with all of the instructions looping around, but that's not a very useful one. You won't be able to prove anything. It will satisfy this property, but will not be very useful. So I want something that contains all of the traces that can be generated by the initial program, but is not too coarse so that I can reason about it. So how do I verify this criterion, that the traces of my program are included in the traces of the control flow graph? So I'm going to do it inductively. So what I'm going to do is to say, I'll take this block of instruction, and I'm going to show that, for instance, the initial state of the program and the initial state of my control flow graph are in a certain relation. And every time I can do, I can execute this block, this segment, I end up at the target address that's defined by the next block. And I'm going to apply the semantics of the EVM to check that for every input state. When I execute this block, the target of the jump is the start address of this segment. And I will do that for all the pair of edges. And then I provide an inductive proof that every time I execute the code in the blocks, in the segments, it can be stimulated by the code in the control flow graph. And that's a proof of trace inclusion in that case. So how does it work in practice? So I'm going to take the code of this segment and encode it into the Daphne EVM somehow. In practice, it's not, I'm not using the actual semantics, I'm using an abstract semantics, but let's say it's the semantics of the EVM. So I'm going to take this code and write it in the Daphne EVM as a sequence of instructions and tracking the state after. So I start in a given state, and I compute the next state. It's a push one, push one, push one, push one. So if you push one, so I'm using the push n with n equals 1 in the Daphne EVM, and I just swap 3, and so on. And I want to check that at the end, in the last state of this segment, after the jump, the program counter is actually 0x1b. So to do so, I could write an assert statement here, which is assert that the PC in S8 is 0x1b. But what I want also to be able to show is that I can execute the code of the next block without any, let's say, underflow or overflow in the stack. So what I'm going to do is to call the execution of the next block in the program to say, after you've computed this effect of the segment, you should continue. So there's a continuation. You should continue to segment 3, node number 1, to execute the code. And this code has actually some preconditions to be satisfied. So the meaning here is that I start my execution. It's the initial state of the EVM. So there's no real condition on the stack. The stack is empty. Well, it's got more than 0 operands. It should be 0, but more than 0 is enough. The PC should be 0, and I should be able to execute this code, and I'm going to verify this in Daphne. So in the semantics of each instruction in the Daphne EVM, there are also pre and post conditions that must be satisfied. So if I'm able to verify this code in the Daphne EVM, it means that there's no stack underflow, stack overflow, and so on, that all these instructions can go until the end. And when I call this, when I go to the next node, to be able to verify the program, I'll have to verify the preconditions that are imposed by the next node, including that the PC is actually 0x1b, which is where this node starts, and that some requirements on the stack are satisfied as well. The stack has more than 5 elements, and some elements in the stack are actually some values that are keeping track of the program counter. So I do that for each edge in the graph. And what I obtain is a proof object, and I'm going to verify this proof object with Daphne. And if it verifies, the control flow graph is semantically correct in the sense that every block, every execution of a block from an initial state will lead to the next block. And because I have proved it for all of the input state, I have an inductive proof that all of the traces of the program are actually included in the traces of the control flow graph. Right, so it's a simple check. I generate this object. the sequence of code for every block with the call to the next block, and I verify this Daphne program, and if it's verified, then the control flow graph is another approximation of sequences of instructions that can be generated by the initial program, the concrete program. Right, so what does it guarantee when I verify again this proof object? It guarantees that all the jump targets have been properly computed, so I have checked that they are properly computed. And it also guarantees, so in my setting here, there's no stack underflow. I can do no stack overflow as well, but I have simplified the semantics here, so I can check that the code in the EVM never has a stack underflow exception. So if you're curious about it as well, so I'll give a list of some blog posts that I've written about it. I'm not actually using the actual semantics of the Daphne EVM, but I'm using a more abstract semantics. And I have proved that this more abstract semantics refines the semantics of the EVM. So what are we'll check if there are any questions at that stage before I go to the limitations. Any questions? So I'll finish by some limitations, known limitations. So there are some, I've tried the dozens of programs, so from simple to, and they are in the GitHub repository of the tool as well. So I can do, of course, a large code like EVM, ERC20, deposit contract, wrapped if, and even larger code. The strategy I have adopted works only if the target of the jumps are on the stack. So there's a program, for instance, this one, sorry, it's a program that was generated by the Viper compiler, where some jumps, some target of jumps are actually pushed in memory. So for this one, this is what my program is doing. It says I couldn't determine the target of the jump because it's not on the stack, so it will abort and not compute the result. There's another one that was given to me at some point. It took me a while to figure out why it was not working. So it's a Fibonacci program, so it computes the Fibonacci series, but it's a non-tail recursive version. So it stacks calls on the stack and unstack them when it reaches the last element. So it turns out that for this one, it's not a failure of the tool, but the control flow graph for this program, it's a non-regular language, so it cannot be represented by a finite automaton. And in the setting that I have, it will reach the maximum depth in my depth search and say that the maximum depth has been reached and will not produce finalize the final complete control flow graph for this program. So right, so what have we achieved? So I would say there's a robust and verifiable control flow graph reconstruction algorithm. So in terms of robust, I've implemented the code in Daphne. So I think there's quite a lot of checks in the code that makes the code reliable. There's no, let's say, division by zero, out of bound, and so on. There's also some verification that I can talk about later on, but I think we're almost out of time. But the control flow graphs that are generated can be automatically verified. So I can automatically generate the proof object and verify it with Daphne. So if you want to know more, the backend, the tool with the backend is at this address. The sort of the interface, the ByteSpectre interface is at the ByteSpectre URL. And there's 2 blog posts detailing what I've been talking about today on the control flow graph reconstructions and how to verify them with the details of the semantics and so on that you can read about as well. So just to, I think it's some of the features of the graph, of the program. I think most of them are easy, but there's one, for instance, which is quite useful in terms of when you want to verify, you can choose the size of the segments as well. So you can reduce them to be able to prove smaller segments using the Daphne EVM. Sometimes it's sensitive to the size of the segments. If you have long sequences of instructions, it can be hard to prove properties about them. So you can decide to limit them to, let's say, 10 or 12 instructions, and the generator will split the code into smaller chunks. it can generate some statistics about the code as well, and so on, print the different segments and a few other things. And things that I've been doing, but it's not finished yet. So proving functional properties, so beyond Stack Overflow and Stack Underflows of the code. So I've got a few examples using, for instance, the maximum, the function max that computes the max and so on. You can actually instrument the proof object to prove that it actually computes the maximum of 3 numbers. But it's probably a better idea to try to prove some sort of a refinement between some higher level code like Yule and the EVM bytecode, and do the proof at the level of the Yule code and show that the EVM bytecode refines the Yule code, or the Yule code simulates the EVM bytecode. A few things that we haven't done yet. So my colleague Egon, he designed this simple user interface for ByteSpectre to demonstrate how the tool works, but it's not polished enough, and there's some resizing effects that are not working properly. So we need to improve on that side as well. And I was planning also to use the proof objects to be able to compute some bounds on the gas costs. So it's not trivial, because the gas costs, when you execute a program, it can depend on the memory expansion and stuff like that. So computing the gas cost is actually an exercise in defining invariants on memory sizes, and that can already be an interesting topic to try investigating. And I think I'll stop there because I'm over time.
Over time due to lots of good questions. So
yeah. Thank you for that.
Yeah. So that was a very interesting talk, Frank. And
thank you.
Yeah, interesting thoughts. Did you get to integrate in those the next slides or next talk slides?
Yes.
Yeah. Okay.
Merch first.
Yes, merch. Yes, sold a t-shirt, right? Hadn't sold one for a few weeks, and then suddenly there was a sale just yesterday. Anyway, next slide. So the forthcoming talks has been shaken up a bit. So hopefully that's not mucked up too many people's schedules. But in 2 weeks, I'm going to be talking about Uniswap v3 liquidity pools, and trying to really get into how should people think about them, because I know we've talked about these constant curve things, but I mean, that's a really highly mathematical, high level view. But, you know, if you're actually going to put a couple of $1,000 into a liquidity pool, how would you set it up? You know, what should you be looking for? Which coins would you really put it in for? Which coins are safe? You know, what should you be, you know, how should all that work? So I'm going to give people a bit of a feel for my understanding, and I'm not a guru on the topic, but I think at least I've got some ideas. Matthew is going to give us a deep dive on layer 0. So that was meant to be today, but it's been pushed out by a month. I'm going to talk about random number generation and talk about the issues that you can have, and how you can do it so it's secure for blockchains and rollups. Andreas Freund is going to come along and talk about another perspective on L2 standardization. And David is going to tell us about how AI and blockchain really intersect, which is going to be super interesting, because I'm interested to see what's happening. So David, just a question, the group that you're working for, is that public, or can we not even mention that stealth group?
That's a fine question, Peter. I have absolutely no idea.
Okay.
I'll find out for you.
Yeah, you should find out before August 21. So David is working on a stealth group that may have something to do with AI and Web3, but yeah. All right, and there's one more slide. Okay, so if you're here today, there is a YouTube channel where you can catch up with the recording. If you're watching this on YouTube, you can join and ask tricky questions live. which is that meetup group link. You can have discuss with the speakers and everyone else by joining Slack. And sometimes there is example code, in which case you should go to that link there at the bottom. So are there any last last questions for Frank?
So, I mean, I have a question if no one else does. So I'm interested in that sort of what you alluded to at the end there, which is actually using the generate or the deconstructed graph to do some analysis with the Daphne EVM. I'm wondering how much progress you've made on that.
Unmute myself first. So I've got a prototype generator, and I would say it's not pushed yet, or it's not completely terminated. Well, it's not complete yet, but I had to add a couple of things, like what I was mentioning, for instance, splitting the large segments into smaller chunks, because the Daphne EVM, when you go over, well, my experiments were about 30 to 40, depending on the instructions. It can't prove anything about the sequence of linear instructions. It's too large. So I implemented this thing to chunk the code into smaller pieces as well. And I had to implement as well some, you might have seen, it's a bit probably tricky, but in the code, there's there's some gas happening. So when we do some proofs, we need to make sure that the depth of the execution is bounded. It can be arbitrarily large, but bounded. Otherwise, because you've got continuations that can call previous, you may have infinite loops. So I had to implement this thing as well in Daphne to be able to reason about arbitrarily deep executions, but of finite sizes. And then otherwise, the code is it's almost ready to go. It's the same code that I'm using for here. I'm using an E state, which is a bit of it's a simplified EVM state. So I've got a sort of a simplified semantics to prove that my graph is correct. But I can replace this E state by an EVM state and start to reason about some code. So I've done that again for a simple program like the computing the maximum of 2 or 3 numbers. But my opinion is that it's not, I would say, it's not very easy to reason about bytecode directly. So that's why I also started this thread on encoding the semantics of fuel in Daphne. And it's usually much easier to prove a sort of a refinement of a chunk of code. So refinement meaning that you start with these values, and at the end you get the values and you relate them to the Yule code, which is a high level code. So do the proofs at the Yule code level and show that the EVM bytecode refines the Yule code. So that's what I was probably trying to do. But I can prove some simple properties of the bytecode.
Cool. Sounds nice.
I posted a question in chat. It's not relevant to the topic. Can Frank comment on the move languages?
Where is it?
The second question.
Can you comment on Swift flavored move and after flavored move? Which one do you prefer? I'm unable to comment on. So Movement Labs will have their own version of move, probably some tweaks in the semantics. So that's the thing.
I see.
Yeah.
Thanks.
I reckon an interesting talk for maybe 3 months' time is you to give us the lowdown on the difference between MoveVM and the EVM, and
there are different things, and so we can try to have a talk on Move.
I think it would be interesting, like, to understand, understand, what's the difference, and why would someone have, why did someone come up with MoveVM, and in what way does it make sense that someone would do that? Because I think it's interesting to be able to see what other ecosystems are doing to understand how they relate.
That's cool.
All right. Look, thank you for your time, Frank. Thank you, everyone,
Thank you very
for
much.
coming along.
Thank you, everyone, for your questions.
All right. Talk later. Bye-bye.
Thank you. Bye-bye.
Thank you.